We now begin our last major unit in AP Chemistry. And this unit on nuclear energy, nuclear chemistry, is the one chapter that focuses on, obviously, the nucleus. If you think about it, every chapter we've done up till now, other than a few pages where we learned a little bit about the nucleus and what it's made out of, because we were concerned about the number of protons, every chapter has been about electrons in one way or another. Because electrons are involved in chemical reactions and chemical bonds and chemical properties. This chapter is all about the nucleus. And it begins with a little historical note using the word alchemy. Alchemy, in a sense, is old-fashioned chemistry. Alchemy is this initial effort, these fledgling attempts to understand the composition of things. And sometimes it had a motivation beyond curiosity. For example, can you turn ordinary materials into gold? Now, as you will find out in this chapter, you can't make gold out of other elements without changing the number of protons in the nucleus, which of course was totally impossible back then. But the point I want to make is this. Sometimes, in fact, all too frequently in 20th and 21st century chemistry, we look back on these early chemists and these early efforts with a little bit of disdain, with a little bit of arrogance. We kind of laugh at what they're trying to do, and we sort of think of ourselves as we know better, maybe a touch of elitism. And the tendency then, and I've seen this so often in my career, is to look back at people in history. And because they didn't know as much as we do, we have a tendency to dismiss them as being somewhat ignorant or simpletons, or, well, they believed in magic. And as a result, we have a tendency to dismiss what they believed as also the same kind of thing. So both, if their early chemistry was silly, so was their faith. And that, of course, is totally presumptuous. And it ignores, for example, many things, such as 50 years from now, people are going to look back at us as being kind of ignorant, and they're going to laugh at some of the things that we think is true. But of course, these men and women of centuries past were making incredible strides and laying a firm foundation for what we do today. In fact, Isaac Newton himself has said, if I appear to be wiser or smarter than some of these people that have gone before me, it's only because I'm standing on their shoulders. But there is genuinely, sadly, a sense of people back then, because they didn't know as much as we do, therefore their faith was just as ignorant as their chemistry knowledge. Complete misunderstanding of faith. And it's an evidence of scientism, a trust in science. Now, we're going to find that nuclear physics and nuclear chemistry shows up in all kinds of modern ways. Our medicine would be way, way far behind compared to what it is today without radioactive isotopes and nuclear procedures. The electrical energy that we get from nuclear plants has been instrumental, along with other sources of energy, to make modern technology possible. And in fact, modern civilization and human flourishing depends upon inexpensive energy, so that even poor people have access to batteries and electrical energy and air conditioning and refrigerators and smartphones and laptops. That should be our desire. And then, of course, you also have the use of nuclear energy in the form of nuclear weapons. Incidentally, we take on a lot of these subjects in greater detail in AP Physics, which all of you should be taking next year. Well, we begin with natural radioactivity. And this science, this knowledge, this understanding is barely 125 years old. It's probably a little bit less. And it kind of started coming into focus about a century ago. And the idea that all around us, there is this thing that we call radioactivity, which has nothing to do with radios. What it does have to do with are these invisible, difficult to detect particles and photons that have an effect. They have an effect on the environment. They have an effect on biology. They can be detected. They can be measured. They can do things. And we didn't know always that they existed. And so when we began to discover these kinds of radiations, natural radioactivity, we began to number them as we discovered them after the opening letters of the Greek alphabet. Just a few years prior, in the 1890s, X-rays had been discovered. X meaning an unknown ray. Well, so that left the end of the alphabet kind of already taken up. So we began to use the Greek alphabet. And the first three kinds of radiation that we discovered, and the ones we talk about today, are alpha, beta, and gamma, the first three letters of the Greek alphabet. And occasionally you'll see a science fiction show, like in Star Trek, where they might talk about delta rays, a hypothesized fourth kind of radiation that so far has not been discovered, and we don't even have any theories about it. But this chart shows us that alpha rays are really particles, helium nuclei, with your 4 nucleons, 2 protons plus 2 neutrons, and your 2 protons, which make it the element helium. So the symbol that you see down here in this chart, you should get used to the fact that the upper left is the number of nucleons, the particles in the nucleus. The bottom left, the number 2, is the number of protons, which is redundant to the symbol. Helium has 2 protons. If you have 2 protons, you have helium. So oftentimes we don't bother with the bottom left number. You already know that if there was a number in the upper right, it would be the charge number. And in fact, we could put a +2 here because this is a helium nucleus without its electrons. And then the number in the bottom right, we typically use for the number of atoms in a formula. A beta particle turns out to be identical in all ways and forms as an electron. What's different is where it comes from. We'll take that up a little bit later. And then the gamma particle is actually a gamma ray, a super high energy photon, even more energetic than an X-ray. Now, a classic experiment in chemistry, and chemistry and physics students should know some of the classic experiments that propelled science forward by leaps and bounds, is this experiment done by Rutherford, where they bombarded a piece of, they took some radioactive materials and they shot them at various targets, and they found out that the alpha particles, the first known particles, the big bulky ones by comparison to the others, could be blocked by a piece of paper. You might remember I did this demonstration in honors chemistry. In fact, your skin would block alpha radiation. Beta particles can go right through paper, but they're not going to go through lead. Gamma rays will go through a 0.5 centimeter of lead and even more, like I demonstrated last year. So you can see that alpha particles aren't very penetrating. Gamma particles or rays are very penetrating. So the penetrating power is important to understand between the 3 kinds of radiation. Not all kinds of radiation are created equal, so to speak. The damage from radiation, obviously, is if it can get inside your body. And of course, alpha particles can't get inside your body unless you have an opening in your skin, we could say injection, or through inhalation, or through ingestion. which are the three common types of ways in which alpha radiation can get, alpha particles can get inside your body. Now, nuclear reactions obey principles, and these principles can be described in a nuclear reaction, where you have the kinds of things that you start with on the left side of your arrow, and the kinds that things that you end with on the right side of your arrow, just like in chemical reactions. There's no equilibrium established here necessarily, though like in chemistry. And this work is a little more than 100 years old, at least the beginning of it. And so here you have your first nuclear reaction in this chapter, where you have a nucleus of radium-226, which means if you take its 88 protons and add all the neutrons that it has, you end up with 226 nucleons. That radium-226 undergoes a decay and turns into a whole new element that didn't exist a moment before, radon-222. And in the process shoots out an alpha particle. On your test, if you are asked to write an equation for an alpha decay, make sure you put the alpha particle on the right side of the arrow. Every year there's a student or two that for some reason puts it on the left side. If it was on the left side, that means your alpha particle would be like a bullet being shot at your radium-226. And that's not what's happening here. Another thing you should know is that just like in chemistry, where the mass of the reactants must equal the mass of the products, in a nuclear equation, the nucleon number must be the same on both sides of the arrow. In this reaction, you have 226 nucleons in radium on the left side of the arrow, and you have 4 from the alpha particle plus 222 nucleons in radon on the right side of the arrow. They equal each other. And the charge number, the proton number, must also be equal. 88 for radium on the left, and 2 plus 86 for radon on the right. Those numbers must equal each other. That means that on a test, if I told you 2 of these 3 particles, you could figure out what the third particle is by following these conservation rules. Now, in this nuclear equation at the top, you have uranium-239 shooting off a beta particle, and it becomes a neptunium-239. This is a beta decay. In an alpha decay, obviously 2 protons and 2 neutrons that used to be in the nucleus, for some reason, get together and come flying out of the nucleus, reducing the number of protons and neutrons in the original nucleus. In a sense, what's happening is this nucleus is becoming a little bit more stable than it was before. But in a beta decay, something strange happens. A nucleus, this case uranium-239, shoots off a beta particle. And a beta particle is technically nothing more than an electron. So where did that electron come from? And how come when you get the product neptunium-239, it has the same number of nucleons as uranium-239 had? What's with that? Not only do you have the same number of nucleons, but your proton number went up instead of got reduced. And the way we understand it is in this equation down here, an equation that just fascinates me. And that is that evidently, for reasons we do not know, reasons that have to do with the structure of the neutron itself, not to mention the structure and organization of the nucleus itself, a neutron turns into a proton and an electron. Now, there's all kinds of implications here. For example, why does a neutron shoot out an electron and turn into a proton? Can we predict when that will happen? Can we make it happen? Can we keep it from happening? And the answer to all of these questions so far is no. We don't know how to do that. Another thing that we might want to think about is, does this mean that a neutron is not a fundamental particle? And the answer to that is probably yes. And I just finished doing a screencast in subatomic particle physics for my AP physics class 2 days ago, where we talk about all of the baryons and hadrons and bosons and leptons. Is the electron a fundamental particle? We think so. Is the proton a fundamental particle? We don't think so. In fact, we think neutrons and protons are made out of quarks, which is not what we need to worry about in chemistry. Now, because a neutron turns into a proton, that's why a beta decay moves you up 1 on the periodic table, whereas an alpha decay moves you down 2 elements on the periodic table. What happens to this electron when it's produced? Well, the electron comes flying out of the nucleus and will almost immediately be captured and become one of those electrons in the shells around a nucleus of some atom. The proton, of course, stays inside the original nucleus. And why this happens seems to have something to do analogous to the energy that we see given off when electrons who have been energized and jump to higher energy states, when they fall back to more stable states, they give off photons of energy. Remember, that was way back in section 6.3 in your book. Well, there seems to be an analogous situation going on in the nucleus, that the nucleus also seems to be highly organized in its structure, so that as particles move to higher energy levels, when they fall back to more stable energy levels, and we're talking here about protons and neutrons, not electrons, something happens. Energy is given off. And this is a whole amazing region of study in nuclear physics. But why should we be surprised that the nucleus itself isn't just a hodgepodge of protons and neutrons, but is also highly organized? And I think that's a fundamental biblical principle and something that Christians should expect, that every layer you go deeper and deeper into the structure of something, you find greater and greater organization, complexity, and design. Now, when we have these radioactive elements, especially these naturally occurring radioactive elements or atoms, they seem to follow one of 4 different pathways as they undergo radioactive decay, which is the process of turning into some other element and as a result becoming a little bit more stable. Things that are unstable, and then for atoms we mean they are radioactive, will gradually become more stable. And they do it by jumps, by shooting off particles like alpha and beta particles. We call the original particles the parent particles, and what they turn into the daughter particles, or the decay products. And they follow one of 4 pathways. And so they usually begin with uranium-238 or some other radioactive element and begin to go through steps. And eventually they get down to a stable isotope of lead. So here are the first 4 steps of one particular decay series, beginning with uranium-238. Step 1 is an alpha decay turning into thorium-234. Step 2 is a beta decay, so you jump up 1 to protactinium-234. Step 3, you do another beta decay, And now you're back to uranium-230, but uranium-234. And then you do an alpha decay and return to thorium, but now you're thorium-230. These are the first 4 steps of many, as uranium will eventually turn into a stable isotope of lead. Each step takes a certain amount of time, which we measure by something called the half-life. And we'll talk about that later. So uranium ore has lots of stuff in it, but it includes uranium-238. In fact, uranium ore, when you refine it to pure uranium, like Marie Curie did, at great expense and ultimately at the cost of her life from leukemia, pure uranium is 99.3% uranium-238 and about 0.7% uranium-235. And we've talked about that in honors chemistry, and it's also in your handout where I discuss the political implications of this as far as nuclear reactors and nuclear weapons is concerned. Here is the full decay series for uranium-238. And remember, there are several other series like this. Now, on your test coming up, you have a periodic table, and I will pick a radioactive isotope of some element, and I will give you part of its series. I will say such and such a nucleus undergoes an alpha, beta, alpha, alpha, beta, 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 alpha, beta, or some such sequence, and ask you, what is it now? And you will have to follow it on the periodic table, remembering that every beta decay turns a neutron into a proton, so you go up 1 on the periodic table. But every alpha decay causes you to lose 2 protons and 2 neutrons. And they all have different half-lives, which you can see in this chart show quite a range. For example, uranium-238 has a half-life in the order of 1 billion years, 4.5 billion years to 2 sig-digs, which interestingly enough is what many scientists think is the age of the Earth, including many old Earth creationists believe that the Earth was created 4.5 billion years ago. So you would expect there to be some uranium with a half-life of 4.5 billion years. The elements that have a half-life that's shorter than that, a lot of that would be gone by now, and those elements which have a really short half-life would be completely gone except when they happen to show up momentarily in the process of this decay series. So you go from 4.5 billion years for some half-lives, and then you can see some of these half-lives are in the microseconds, like polonium-214. I mentioned Marie Curie and her monumental, mammoth work of being able to come up with a single gram of radioactive radium by processing 7 tons of ore. Remember, 7 tons of ore, these are metric tons, would be about 15,000 pounds. That's amazing work. Now, radon, if you go back to that periodic table, is the one element in this decay series that's an inert gas. So instead of being chemically bonded in some way with some of the other elements or interacting or trapped, radon as a gas will begin to work its way up through the Earth's crust and can escape into the Earth's atmosphere. Now, alpha particles, if they get up into the Earth's atmosphere, well, the alpha particles, even before they do that, will pick up electrons and become helium nuclei, which being inert, creates the helium that we find in trace amounts in our atmosphere. It's continuously being produced. But the radon as a gas can get trapped in buildings, especially buildings that are highly insulated. And so radon, being denser than air, has a tendency to collect in the basement of well-insulated buildings or in low spots. And radon, because it can exist for a while and is continuously being produced, can get breathed in. And that means that you are introducing into your lungs an alpha emitter. You can see by the two equations here that you get alpha particles. And these alpha particles, being very large particles, are ionizing. Even though alpha particles don't penetrate, if they can get into your lungs, they can do a lot of damage because they're ionizing. They're moving around, knocking electrons off of other molecules and breaking chemical bonds, and as a result, creating ions and destroying molecules like proteins and breaking DNA structures. So that's why they're so dangerous. An alpha particle is like a bull getting into a china shop which sells delicate glassware and vases or vases and porcelain and things that are very, very fragile. A beta particle would be like a big old bumblebee getting inside. You would expect a bumblebee to be able to get easily into the door of a china shop, but not a bull. A bull would do a lot more damage, but its penetrating ability to actually get in the door is unlikely. Bees can get in, but they're not going to do as much damage, and a gamma ray would just be like sunshine coming in through the window of your china shop. And by a china shop, I mean a shop that sells china, which would be teacups and saucers and glasses and plates and other very expensive and fragile dinnerware. So if you have lots of radon in your basement, nowadays when you get ready to sell your house, besides having a termite inspection and other kinds of inspections, you would have a radon inspection. And that radon inspection would measure to see what the levels of radon are in your basement. Because radon is a very, very distant second to cigarette smoking for causing lung cancer. Nothing comes close to cigarette smoke as far as lung cancer is concerned. And you can buy radon detectors at your hardware store. And if you do have high levels, then all you need is a radon mitigation system, which basically circulates the air in your basement with the outside, basically a fan through a PVC pipe. Now these radioactive decay series go through alphas and beta decays, and each step of the way it gradually becomes more and more and more stable until eventually you finally reach a stable isotope where it ceases to decay. And that would be a stable isotope of lead. Now there are other kinds of radioactive decay, some of which we don't really see except in our fancy particle accelerators or in the upper reaches of our atmosphere when cosmic rays smash into particles, or we see them sometimes in nuclear reactors. But we do see, for example, times when instead of giving off an electron, a beta particle, it gives off a similar particle that has the opposite charge. And so you see that down here. You see the Greek symbol beta. And remember, this is an electron, same mass, but it's positive instead of negatively charged. It's the opposite of an electron. Opposite of an electron is not a proton. Remember, a proton has a mass of 1,836 times that of an electron. And a neutron is 1,837 times. So if you think about a neutron being 1837 minus a proton, which is 1836, what's left is a particle with a mass of 1. By comparison, the electron. Well, this is the opposite of an electron in terms of being a +1 instead of a -1 particle charge. It's called a positron, and in fact introduces you to a whole series of particles that we call antiparticles, which make up a category of matter called antimatter. And again, that's something we talk about in AP physics. Anytime a particle of matter, which is what we've been studying all year, interacts with a particle of antimatter, something called annihilation takes place, and that produces a huge amount of energy. In fact, that is what powers the Starship Enterprise on Star Trek. How are they able to travel, in a sense, faster than light? They're not really going faster than light, but they're jumping through space by warping space. And you warp space by creating these huge amounts of energy. So you can jump across a fold of space. All theoretical and hypothetical, of course. Another nuclear process is called electron capture. It's the opposite of beta decay. You can emit a beta particle, but you can also absorb an electron as well into the nucleus. It's called K capture, by the way, because way back when, and this even precedes me, so you know it's old, the innermost stable shell of an atom was called the K shell. And this is something you should be able to do, and you will have to do it on a test. In any nuclear reaction, you should be able to be given 2 of the 3 particles, and you should be able to figure out what the other particle must be, in this case where the question mark is, because the nucleon number in the upper left must add up, and the charge number in the bottom left must add up. And if you think that might be a challenge, I encourage you to practice that. Now, some atomic nuclei are stable, and lots of atomic nuclei are unstable. Unstable means they're going to become stable. Unstable means they're radioactive in a sense that they are going to shoot off particles at some time that we cannot necessarily predict, so we have to talk about statistically. When we go to graph all of these nuclei in terms of looking at their proton number and their neutron number, we learn some interesting things. And this is in the chart on the next page called the band of stability. So if I go to the next page, this is the chart we're going to look at and draw some observations from. This is the chart that is actually on the wall behind my chair in my classroom. It doesn't look exactly like this, and it has a whole lot more information than this does. The solid line that you see there in black is the line where you have a slope of 1. Neutrons in the y-axis, protons in the x-axis. So when the number of protons equals the numbers of neutrons, n, which is the neutron number, divided by z, the proton number equals 1. And this band of stability, you can see, begins with a slope of 1. And about the time you get to the element calcium, element number 20, you can see that this band of stability begins to increase and no longer has a slope of 1, but has a slope of greater than 1. So let's go back and look at the bullet points. The band of stability, which is this graph of about 1,500 isotopes, about 230 or 40 or so of them, or maybe as many as 300 are stable. Different books say different things. It looks like your book is using the number up here, 300 stable isotopes. So the other 1,200 isotopes are unstable, are radioactive. Now, so there's bullet point number 1. Bullet point number 2, there's only 2 stable isotopes that have more protons than neutrons. And if you think about it, as soon as you have 2 or more protons in the nucleus, you know they're going to repel each other because protons are positively charged. And the way you can mitigate that Coulombic electrostatic repulsion of like charges is by having the protons separated with a neutron in between. And that works somewhat for the smaller nuclei. But eventually you need something else to hold the nucleus together. You need some type of strong nuclear force. And we'll talk about that later. Bullet point number 3, I already mentioned. After calcium, you need more and more neutrons compared to the number of protons. Bullet point number 5. After bismuth, element 83, the element after lead, beyond bismuth, every single isotope is unstable. You do not have any stable isotopes. And at this point, you need some kind of nuclear superglue, which we actually hypothesize is mediated by a particle called the gluon. And that's, again, AP physics. Have some pretty interesting names. The next bullet point. Isotopes that fall farther from the band of stability have shorter half-lives. So the farther away you get from that band of stability, where the black boxes are, either above it or below it, the shorter the half-life. Now, we also have some rather interesting observations. The last bullet point on this page, elements of even atomic number seem to have more stable isotopes than those which have an odd atomic number for some strange reason. Now again, look at those black boxes. All the red boxes above the black boxes seem to decay primarily by beta emission. That means one of their neutrons turns into a proton, and out comes the electron. All the red boxes below the black boxes seem to decay primarily through alpha decay. They shoot off 2 protons and 2 neutrons. And of course, as long as you're getting rid of protons at some point, you're going down the periodic table, heading towards lead. And again, I hope you look at these nuclear equations and become very comfortable talking about alpha decay, beta decay, positronic emission, K capture, electron or beta particle absorption, and so forth. Now, I mentioned that these neutrons aren't sufficient at some point to hold the nucleus together. There is something else going on. This is called the strong nuclear force. This is called the nuclear binding energy. And the nuclear binding energy comes from the fact that some of the mass of the nucleus itself turns into energy to keep the nucleus intact. And we can calculate this energy using the equation E equals mc squared. And we'll start talking about this in the next screencast.